So in the previous video, we mentioned that if you have a box of atoms, and the box is isolated from the rest of the universe, and you have these atoms moving around in a kind of random fashion in the box, we call this a NVE system, a system with fixed number of particles, fixed volume, and fixed energy, right? And we know that we can describe the state of the system using the so-called microscopic state. So the microscopic state is just a collection of all the positions of the particle and then all the velocity of the particle at a particular time point t. And we know that if we know these information, right, we can advance the time by a small amount and then predict what the system gonna be at a later time. So we call this the microscopic state of the system. And also we introduced the concept of phase space, which allows us to schematically map every single microscopic state into a diagram which composed of many axes. Here we show a two-dimensional schematic of that phase space where we consider that horizontal axis represent the collection of all of the positions, and then the vertical axis represents the collection of all of the velocities. Right? In this setting, you can map a particular microscopic state as a point into this phase space. Okay, so now we imagine that if the particles, or if the system is evolving, right, the particles is moving around, they're changing the positions, they're changing the velocities, right? If we keep track of that evolution of the system, and in particular, we take a snapshot at each time point, and for each time point, we can get a set of numbers which represent the microscopic state of the system, and we can map that number into the phase space. So as your system is moving or evolving in the real space, right, we're gonna get a series of dots in the phase space, and these dots represents the evolution of the system, right, but in a different setting, like in the phase space. Okay, so this is what we already described in the previous video, so you can go to look at that video for details. But for now, we just do a very quick recap, right? So now with this background, what is an ensemble? Well, an ensemble is simply a collection of all of these microscopic states of the system, right? We know that when the system is evolving, it's visited many different microscopic states. Now we have these states mapped to the phase space, and we collect all of the states. This is called an ensemble. Okay, so now for a system with fixed number of particles, fixed volume, and fixed energy, we call the collection of all of the microscopic states for such a system a microcanonical ensemble. Okay, so the question is that why we want to introduce the concept of ensemble? Well, okay, you know that for a physical system like this, what we're interested in is some average properties of the system. For example, I'm interested in knowing that what is the average energy of this box, right? Now, of course, for this particular system, the average energy is very trivial. It's just given by this fixed energy, right? But we can still use this as an example to show how we're going to use the ensemble average. So again, the idea is that what is the average energy of the system? Now, we know that the system is evolving, right? So the energy of the system, in principle, is a function of time, right? Because at each time, the particle is a different location, they have different velocity, so they have probably different energy. Now, of course, in this case, energy is the same, so it's a bit trivial. So the average energy then is basically, you just take the average, right, of the sky. Suppose that we observe the system for a certain period of time, from 0 to capital T, right? And then we just average the time-dependent energy over this time, and then we can get the average energy for the system. Okay, now let's look at how this is reflected in the phase space. We know that as the system is evolving in the real space, right, it's actually visiting different state in the phase space. Maybe it's starting from this state and goes to this one, and now goes to this one, and so goes to next one, and then basically visit all the states in a sequence. So in certain sense, when you do the time average of this particular energy, from the perspective of the phase space, you're doing another average, right? You're taking each of this particular state And for each of the state, you can have an energy, which we call ES, where the subscript indicate a particular state. Right? So in this case, what you can say is that, okay, then the average over time is simply equals to the average over all the state in the system. So this is the total number of state we denote by omega, and you sum over all the states. This also gives you the average energy of the system, right? So now you see there are two different averages. Now this one is what we call the time average, and then this one is what we call the state average. Okay, but then if you look at our illustration, right, for the state average, we're starting from the initial state and we basically follow the evolution of the system. So we visit each state in a particular sequence until all the states are visited, right? So basically we go from this particular sequence, and then for each of the state, we basically compute what is the energy for the state, and then we average this over all the state. Now here is the question, right? Do you really have to follow the sequence of all of the states to compute the energy? Can we do something else? For example, I visit this state first, and then I jump to another state, and then I jump to another state, and then I jump to another state. I just randomly sample the states. But as long as I sample all the states in the system, right? It doesn't really matter what is the order that I sample the state. As long as I sampled all of them, you're gonna get exactly the same thing, right? So you get exactly the same state average. It doesn't really matter whether you go this in a sequence or you just sample the state in a random fashion. Now this is the idea of the ensemble average, right? So we want to compute some average property of the system, which depend on the states, right? We know, a more intuitive way to do this is to get a time average, right? But as time goes on, we know the system is visiting different state in the phase space. So the time average now is equivalent to the state average. And then a very natural analog for do the state average is to visit each of the state according to the sequence. Just the same sequence that the system visits each of the state. But now we know that we don't have to do this following a sequence. We can sample the states in a random fashion as long as all of the states are visited, right? That is the idea of ensemble average. So basically, an ensemble average is a way to compute average property of your system, and you compute these properties by randomly sample the states. Now, as long as you get all of the states, it doesn't really matter what is the sequence you use. Okay, so that is basically why we introduce statistical ensemble. It provides a very convenient way for us to compute average. Now, there is a fundamental assumption for this, and the assumption is that a system is in thermal equilibrium. Okay, so under that assumption, it doesn't really matter what is the order that you sample the states. As long as you get all of them, you will always get the correct calculation of the property of interest.